This video is about the qualitative effect of fluid resistance on projectiles. Earlier we learned about projectile motion and also about fluid resistance. In this video we'll combine these two concepts and learn how fluid resistance affects projectile motion. It is important to point out that in the IB physics course, we only deal with the qualitative effect of fluid resistance on projectiles, so no calculations are involved. Imagine that a projectile, so for example a small stone, is launched at an angle to the ground in vacuum. Then the same projectile is launched at the same angle to the ground with the same initial velocity, but this time in air or in another fluid. Here is how the two trajectories look like. We'll denote the horizontal position as x and the vertical position as y. I'm sure that you've already guessed that the blue trajectory is the one in vacuum, and the red trajectory is where a drag force acts on the projectile due to the presence of the fluid. Before we compare the two situations in more detail, let me denote the horizontal distance traveled, in other words the range in vacuum, as d, and the maximum height in vacuum as h. I will use a table to compare the motion of the projectile in vacuum and when there is fluid resistance. A difference that we clearly see on the diagram is that in vacuum the trajectory is a parabola. However, when there is fluid resistance, the trajectory is not a parabola. As we already said, the range of the projectile in vacuum is d, and logically, when there is fluid resistance, range will be less than d. The same thing applies to the maximum height reached by the projectile, because logically it is smaller when we have fluid resistance. Recall that when we learned about projectile motion earlier, we examined the vertical and the horizontal motion of the object separately. We saw that in vacuum the vertical acceleration of the object is constant. In fact, this acceleration is the acceleration of free fall. Now when a projectile is moving in a fluid, vertical acceleration is not constant. In a moment, we'll discuss this in a bit more detail. Finally, we also learned that in vacuum, horizontal velocity is constant. However, when we have fluid resistance, horizontal velocity is decreasing. Put differently, there is horizontal deceleration. I think that the first 3 points in this table are straightforward. However, it might not be fully clear to you why vertical acceleration is not constant and why horizontal velocity is decreasing when there is fluid resistance, so we'll explore these 2 points in a bit more detail. Let's begin with vertical acceleration. Vertically, the projectile is either moving upwards or downwards. In both cases, two forces act on the projectile. These forces are the gravitational force and the drag force. When the projectile is moving upwards, both the gravitational force and the drag force point downwards. Therefore, in this case, the net force on the projectile is larger than the gravitational force. Therefore, the acceleration of the projectile is larger than the acceleration of free fall. The exact magnitude of the drag force, hence of the acceleration, depends on different factors. We'll learn a bit more about the drag force in topic A.1.2. When the projectile is moving downwards, we still have the gravitational force that is acting downwards. However, now the drag force is acting upwards. As a result, the net force on the projectile is less than the gravitational force, so the magnitude of the projectile's acceleration is less than that of the acceleration of free fall. Finally, let's see why the projectile experiences horizontal deceleration. While the projectile is in the air, it has some horizontal velocity. As a result, a drag force acts on the projectile in the opposite direction. Since this is the only horizontal force that acts on the projectile, logically, the projectile experiences deceleration. So with this, we have completed our learning about the qualitative effect of fluid resistance on projectiles.